My goal is to introduce a new atmospheric model that may be helpful in wind resource assessment in the future. Today, WRF is the atmospheric model preferred in the wind industry. Both ends of the modeling chain have been improved greatly. We now have better macro-scale input data, like with reanalysis like ERA5, and we can reach higher resolutions with microscale models like WRF LES. In this presentation, I am going to introduce MPAS and some of the differences it has with WRF, and I'm going to show a validation of MPAS and WRF models in model time series with real-world data. At the end, we're going to talk about some of the limitations the current model has. So MPAS stands for Model for Prediction Across Scales, and is a collaborative project led by teams led by a team of US research centers that aim to establish a common framework to simulate the atmosphere, the ocean, and other Earth systems in a way that is smooth across scales. NCAR, the creators of WRF, are the ones leading the development. Of the atmospheric core of MPAS, and therefore EDMA's atmosphere inherits many of the physics suits and the methods of its predecessor. The defining characteristic of MPAS is its unstructured two-dimensional horizontal mesh. Mathematically, a global mesh is called a spherical centroidal Voronoi tessellation, and regional meshes are cut from these global meshes. The smooth transitions between high-resolution areas and low-resolution areas give the desired downscaling, allowing for interaction between scales. To obtain these cells with different sizes, we go through an interactive process that generates a valid mesh from a user-defined density function. The MPAS model was created to solve some of the WRF limitations. For example, MPAS model was created to solve some of the WRF limitations. For example, in WRF there is deformation due to projections. And also in WRF, high resolutions are reached through nesting, which gives flow distortions at nest boundaries. MPAS grid refinement structure avoids those issues and helps have better interaction between scales, amongst other problems. So in wind resource assessment, we need to ask which kind of MPAS meshes would be interesting for us. Taking into account that what we want is to have high-resolution simulations in a small area, we would like a mesh that reached high resolutions and then smoothly transition to a lower resolution of the reanalysis input, for example. And since we need long-term data, we need that these meshes are not very big, do not contain a lot of cells, to reduce the computational costs and time. But we are not there yet. So MPAS still does not release a mesh generation tool, and we only can download the meshes which are available. MPAS provides with some quasi-uniform resolution meshes, which is the cells are all of them are more or less the same size, and it can range from 480 kilometers to 3 kilometer resolution. And then they also have some variable resolution meshes, which the user can rotate so that the high resolution central area is centered at any point. So the best available candidate right now would be a variable resolution mesh that reaches 3 kilometers and goes up to be 60 kilometers. But the central region, the central high resolution region of this mesh is so huge that it takes too much, it's too time consuming for our current purposes. So we cannot do the ideal test of MPAS that we would like to do, but we still wanted to make some tests and to be able to compare some of MPAS simulations with WRF simulations. So what we did was to choose 23 sites around the globe, and we did 4 simulations by site, each of them 1 year long and using ERA5 reanalysis. Of these simulations, 2 of them were done using MPAS and 2 of them were done using WRF. The MPAS simulations were regions, circular regions of different radius, cut from a quasi-uniform resolution mesh. So here we could not use a variable resolution mesh because there's none of the available ones was useful for this test. And then in the WRF test, the difference is that we used nudging in one of the simulations, and we didn't use nudging in the other. So nudging is an option available in WRF that is used to control the simulation using the reanalysis values, and not only as boundary conditions, but also to keep the simulation in some values, the reanalysis values. And this option is not available in MPAS, but we wanted to know how does MPAS compare to both WRF with and without nudging. So these are the results of the mean wind speed bias. I don't think you can maybe read the table, but I think with the graphs, it's more or less the idea. We have high bias, which is expected due to the resolution. And what we can see from now is that the MPAS results seem to be spread wider than WRF, and they are very similar for both simulations, for both the green ones, the MPAS ones, 15 kilometers and 10 kilometers resolution. But more interestingly, we wanted to look at the correlation with wind data, the correlation of the time series. And here we found something surprising, which was that the MPAS simulations performed way better than WRF without nudging, and they also did mostly better than the WRF with nudging, especially with monthly correlations. And here I want to show in a bit more of detail. So these graphs represent the 23 stations that we use for comparison, and the monthly correlation is plotted for each of the 4 simulations we did. And I want you to notice that there are 3 stations where the orange line, which is the WRF without nudging, has very low correlation, lower than 0.4. And in those cases, the yellow line, which is WRF with nudging, improves the monthly correlation. And in these cases, the MPAS simulations that do not have nudging did much better just without the nudging. So this was something surprising and interesting to know. And we also realized that there's one station that the opposite is happening, right? So that in this station, the WRF without nudging actually performed better than any of the other 3 simulations. So there's nothing definite here, but it gives an idea of maybe some specific sites in the world where MPAS and WRF behave very differently. Some notes about the computation and about the computation time. When we did the test, it was a test that run MPAS only using one core, even though MPAS is prepared to be run in parallel, just because to try it in our system was more consistent to do it distributed. And what we did was do one simulation for each day of the year with 6 hours to spin up. And here you have some comparison of the time it took to run. It's more or less the same, right? But MPAS takes a little bit longer. So to run the 15-kilometer resolution, it takes 15 minutes for each day, and 18 minutes if you will want 10-kilometer resolution. Whereas in WRF, it only takes 12 minutes. You can also notice that in the grid preparation time, there is some extra time in MPAS that it's needed to create the grid, to initialize the mesh, and to cut the regions. So, summing up, what we know about MPAS is that we have some limitations and some doubts that we want to be addressed. For example, the available meshes only reach 3-kilometer resolution, while in wind resource assessment, we want to go further than that. And also the available meshes right now contain many cells and are not exactly the ones that would be suitable for wind resource assessment. Also, there is no nudging available. Maybe that's an option that would also be interesting for us. And for now, MPAS does not seem to go faster than WRF without parallel computing. So that wouldn't be a reason to change from WRF to MPAS. So the interesting ideas we have is that there is some hope that maybe using parallel computing, we can run MPAS in a more efficient way. And especially, we really like the excellent monthly correlations we got from that little test. And this gives us hope that the core idea of MPAS, of suitable transport of information between scales, may actually be helping a lot in the results. So there are new versions of MPAS. We are going to be interested in that and ready to make new tests and follow what are the new ideas there. And to sum up, WRF is not going anywhere. It's going to be still the preferred atmospheric model. but maybe MPAS will have something to say in the future and will bring new possibilities to the industry. So thank you for your attention, and if you have any questions, I'll be happy to answer.
Thank you, Marta, for your presentation. And yes, we have already some questions from the audience. Let's start with Zachary. Says, thanks for the great presentation. You mentioned that you are surprised that MPAS performs better than WRF by some metrics for some sites. Why is this surprising? And could you speculate on key drivers of the difference in performance?
Okay, so it's not that I'm surprised. It was just those specific places where WRF without matching really performed very poorly. So it was something that it looked like really special places. There was something weird was happening. And then to try a new model with some limitations and have those special places that you know that don't work in WRF work extremely well with MPAS gives you hope, and it's just like a good idea that makes you think that maybe the way that the downscaling was done in MPAS actually helped the model capture what WRF was missing. So it was this idea that this new way of downscaling was actually helping in some places where WRF was lost.
Okay, Marta. Next question. Can you explain more about data simulation method? What are the observation sources and heights?
Okay, so I don't understand about the data simulation. So it was a data validation, right? So we had some wind data for 1 year in specific locations in the world, different heights. I didn't include the information in the tables to make it more clear. And we used those information to validate the simulations. But in the simulations, what we used was ERA 5 data.
Okay, I think the question goes into that direction in the sources of data you use to initialize the model, and if you use real observations to...
Exactly, I think that's why the simulation is a bit confusing.
I think we have time for...
Confusing.
I think we have time for another question, last one. Thanks for these interesting results. What is the range of data periods used for those 23 stations across the globe?
It was pretty much the same on the early 2010s, I think. More or less all the data stations were the same years, but it was the data we had available. It wasn't an extensive study. It's only 23 sites. And it's mostly this 2015 and so on.
Okay, thank you, Marta. We don't have time for more questions, even we have still some. Let's see, we have time at the end of the session. Otherwise, we will forward to you as with the other authors. So thank you, Marta, for your presentation.